Hi everyone, this is a lecture for chapter 5.6, which covers diffusion and osmosis, which is a core concept on how material is transported in and out of the cell. This corresponds to pages 88 through 89 on your textbook, and we're going to review how water and solutes passively flow, meaning without the assistance of energy, in and out of the cell and in and out of the environment. So I just want to remind you that the membrane itself in a cell is selectively permeable, and in particular for a cell, because it's made of a lipid bilayer, the things that are permeable most easily permeable across the membrane is nonpolar materials, meaning lipids, hydrocarbons, stuff like that. And the smaller it is, the better it is also able to cross the membrane. And sometimes small, very small polar molecules can cross, but not very easily. And generally speaking, things are very charged and very large and charged are going to have a difficult time getting past the membrane. So sugar tends to bounce off the membrane, and salt tends to bounce off the membrane without the assistance of things like transport membranes, which we're going to talk about their role in transport in the next lecture. But of the things that can cross the membrane, they operate through the principles of crossing the membrane via diffusion, and if they can't cross the membrane, then something that's going to influence the flow of materials is osmosis. Okay, so with diffusion, for materials that can simply pass through the membrane or simply pass through the environment, this is a tendency for molecules to spread out evenly into the available space, and thus what happens is molecules will actually move, naturally speaking, in the environment from areas of high concentration to areas of low concentration. A really kind of gross graphic example of that is, think of a fart. If someone farts, it smells very strongly nearby them, but give it a little bit of time, it'll slowly drift and diffuse through the air and spread out further, but not as concentrated as before. And that's effectively what happens with any material that's highly concentrated. It will naturally drift out and spread out more evenly throughout the environment that it can go through. The movement is fairly random, but ultimately what ends up happening is you get to this nice equal-ish spread. All right. Now it's not this perfectly ordered spread. It actually looks more like this, but that's the basic idea. For those of you handwriting your notes, one suggestion I do is this is kind of like a really simplistic picture of diffusion that I like to do, where I just showed diffusion going from this example to a more spread out example. All right. Now, for nonpolar materials that can pass through the membrane very easily, that can cross that fatty acid internal region of the bilayer, those materials, those nonpolar materials like hydrocarbons, like lipids, they pass in or out of the cell simply due to the concentration of the concentration difference. They pass back and forth due to diffusion. So if there's materials on either side, they're going to spread out in such a way through diffusion so that they are more equal than before. So if you look at this picture here, you'll see that there is 6 lipid molecules on this side, and there are 8 on the outside region of the cell, because it's the outside of the cell that it's labeled. So which way is the lipid molecules going to move? Well, it's going to move so that it's more even across both sides. So let's say this lipid molecule moves across, then this would be the end result. Okay? So that you get a roughly equal spread. Now here are some terms that are going to come up quite a lot in these notes today and in the next notes. So the term concentration, just to remind you of it, is the amount of substance per defined area or defined amount of stuff, the defined amount of solution, the defined space, whatever. Now there's many ways to measure it, but one of the more common ways we measure it is we might use a term called molar, and you don't really need to know much about it. You're going to go into super depth on how to calculate molarity in chemistry, but as long as you recognize 0.3 is less concentrated than 2, you're good. It just means there's more solute in the thing with a higher number. Likewise, we might use percentages, but again, as long as you recognize that 2% is less concentrated than 10%, you should be fine. Now, another term we're going to use quite a bit is a term called concentration gradient. So this refers to differences in the concentration from one region to another region. So If this region is a high concentration and this area is a lower concentration, the concentration gradient is going to go towards the natural flow of things. Because in diffusion, things naturally go from high concentration to lower concentration. They spread out so that it's more evenly balanced. Then what that means is the natural flow is towards the low concentration region. So we tend to say that when things move the way they should, when they move from high to low concentration to where there's less of that material, they're going with or down the concentration gradient, because you're going downhill is going with the natural flow of gravity. And if you're going against that, then we say you are going against or up the concentration gradient. So concentration gradient just refers to, hey, there's two solutions with different concentrations. And if you're going with it, then you're going where diffusion means you to go, which is the lower concentration region. Okay? The term with and against, or down versus up, is gonna come up big time in the next lecture. That's why I want to bring that up now. But as far as diffusion and osmosis is concerned, we're mainly just dealing with the normal way things work. So today's notes is all about going with the concentration gradient or down the concentration gradient. So in terms of diffusion, when we go down the concentration gradient, we go from more concentrated to less concentrated. So no work needs to be done here, meaning we don't need energy, we don't need expensive energy from the cell to get this to happen. This is called passive transport. So the cell has the ability to go against the natural flow of things, but in that case, you're going to need energy like ATP, but we're going to save that for the next lecture. Now, I showed how things moved in a free and open space, but when a membrane is involved, as long as the material can get through the membrane, it's still going to diffuse. So in this case here, diffusion of the solutes across the membrane, as long as the holes are big enough for the solutes, it'll still diffuse from high to lower concentration. When there are two separate substances, as long as both can pass through the membrane, they'll diffuse across the membrane independently. So if you notice, the purple is way more concentrated on the right side, so it's going to diffuse to the left over here, or more of them are going to move towards the left, while the orange stuff is going to have their guys move more to the right. But at the end, there's roughly a decent balance on both sides of both materials. Now, osmosis is what occurs when the solute can't cross the membrane. So in order to compensate for the fact that the solute can't cross, the diffusion of water is going to flow in such a way to balance things out. So in this case, and just reminding you, water passes through transport proteins because water is polar, so we have naturally made holes in the membrane that fit specifically water. So it's called an aquaporin, but it's just a fancy word for saying a transport protein for just water. But either way, you have a ton of these transport proteins just for your water. But when other material can't pass the membrane, then what ends up happening is water flows to balance things out. And they still flow from high to low concentration of water. But what that ends up actually doing is water moves to where there's a higher concentration of solute. They will water down what I call the saltier side. So that throws students off because they go, wait, diffusion is from areas of high concentration to low concentration, and that is correct. But for water, it's going from high concentrations of water to lower concentrations of water, but what that ends up meaning is they move to the side with more solute to balance it out so that it's got more of the same concentration of water to solute on each side. Basically, if you think about it, diffusion is about making it as even as possible, but in the case of diffusion, the solute can move very easily, while with osmosis, it's about making both sides as even as possible, but in this case, only water can diffuse, only water can move, and unfortunately, because only water can move, it has to move towards the saltier side just to balance things out. This is very effectively demonstrated in something we call a U-bar or a U-tube, but basically what ends up happening is the water is going to move through the holes, but the holes, the selective permeable membrane is not capable of moving the actual solute from one side to the other, and as a result, only the water can move to the other side to balance it. But then you get to actually see very visually if you fill up a U-bar on each side, and you fill up one side with one solution and the second side with a different solution, like solution A versus solution B, you can actually see based on which side rises higher, which one has more solution versus the other, which is a very effective way to check for the concentration of a solution without actually being able to measure the exact amount of salt or sugar ahead of time. This is just a different image of what's going on, but basically, like we mentioned, water is moving from areas with high water to less water, but it is moving to where there's more of the solute to balance it. Now, we want to use some terms to refer to the side that's got more salt, solute, sugar, whatever. So we use the terms, some comparison terms. So they're not permanent terms. They are comparing one side to another. Okay? So this side, because it has less solute than this side, we call it hypotonic. The side with more solute is called hypertonic, or the solution with more solute is called hypertonic. And when both sides have roughly equal concentration of solute to water, we call it isotonic. So instead of you having to say it's got a higher concentration of solute, you can just say it's hypertonic. That's why we use these terms. Now in this case right now, you see water is flowing towards the right where there's more solute, but that's actually a little bit of a simplification. This is what we call net flow of water. In fact, what's actually happening is water is moving both ways, but is moving at a much faster rate towards the saltier side. Okay? So, while the net flow of water is to the hypertonic side to water the hypertonic side, there's still a little bit of water going towards the less salty side, the less concentrated side. But overall, we're getting a net or flow towards the right. Sort of like a company can be profitable even if they lose some money, as long as they gain more money overall. Now, net flow, like I said, always towards the saltier side occurs to get that nice balance. But eventually, at some point, there won't be a shift. They will have exchanged enough water towards the saltier side that both sides are roughly equal. So does the water just stop moving at all? No, it's still moving. Liquid molecules naturally flow around, but instead there's not a movement that's going to lead to a concentration difference. It's going to actually just stay equally concentrated even though water is flowing back and forth. So molecules can cross in both directions, but there is no overall change at the end of the day. So there's no net flow, but there is some flow back and forth, just the equal amount towards both sides though. So this dynamic equilibrium is basically whenever both sides are isotonic, but there is a unique solution where you can have unequal concentration but have no change in the amount of water on both sides due to cell walls in plants, and I'll show you what happens in those cases. So this is an image of equilibrium, all right, to show you that, hey, some cells will move to the left, or sorry, not cells, some material will move to the left while some material will move to the right. And for those of you kind of hand drawing your notes, this is like kind of over on this side, I kind of gave you a cartoony version of a way to demonstrate osmosis if you'd like. So what does this actually mean for the cell? Well, in this case, because water is going to always flow to the saltier side, this can be kind of dangerous for a cell because a cell's membrane has a limited amount of volume it can accommodate without, time to make more phospholipids. Imagine it as a balloon. When you add water to a balloon, it can accommodate and stretch to a certain degree, but after a certain point, it's going to reach its limitation and pop. And that's what happens if we're not careful. So with a cell, tonicity is very important. The balance and of water on both sides is important. So tonicity is just a special term that refers to, isotonic, hypertonic, hypotonic, the level of solute concentration that's in the environment. Now, if you're an animal cell, that's very critical, because what actually happens is because you lack a cell wall, what that means is your membrane, if water flows too much into your membrane, you have the potential for your membrane to pop. Because remember, your membrane is a little bit limited in terms of how much it can stretch. So what happens is, if an animal cell ideally should be an isotonic solution, that's normal for it. And in fact, our bodies is all about regulating our water intake and removing excess water if that happens, to make sure our concentration in our blood and the liquids around our cells is at the right level of saltiness, that the outside of the cell is roughly balanced with the inside of the cell. However, it can be bad if you go one to either extreme. So if you are in a hypertonic solution, if you are dehydrated, what ends up happening is there is more solute on the outside of the cell, and as a result, the cell can shrivel. In extreme situations, if you shrivel enough, the cell dies. However, even more dangerously is if you have too much water in your system, what ends up happening, especially if your body doesn't have time to remove that excess water, is your cells can be then surrounded by this watery solution. The outside is less concentrated than the inside, so the water wants to rush into the cell, and it just fills and fills and fills the cell until they burst, and then your cells die. This is a major reason why when you do really active sports, even though you may drink water if it's a short amount of activity, if you're doing a large amount of activity like a major football game or a marathon, you're generally encouraged to drink water with electrolytes like Gatorade, Powerade, whatever, because that provides enough saltiness in the water you're putting into your body that you don't overwater your body and potentially cause cell damage. There's also these horrible challenges that have been on TikTok and Vine in the past and stuff, where people were just chugging water really fast. Sometimes that's part of some college rituals and stuff in clubs when they're hazing people, and that's actually extremely dangerous. People have died from chugging as much water as possible, because what happens is their body swells up with water, they don't have time to remove that water, and as a result, their blood cells pop, and they also get some swelling in their brain, and that can cause them to stroke out, etc. Now with a plant, it's a little bit of opposite world. In this case, they actually isotonic solution, equally balanced, is not their ideal form. They actually want what's called hypotonic solutions. That's why your plants kind of tip over and start wilting until you give them a nice glug of fresh water, and then they pop nice and firm up. And the reason why that is because with plants, they don't have internal skeletons like us. So what they do have, though, is cell walls. So they can actually fill their cells completely, and they don't burst because their cell walls prevent bursting. So they actually prefer more water because they get to inflate and become extra firm and extra plump. All right? They don't have the risk of popping, and that extra firmness and extra plumpness gives them more structure, more internal rigidity. So they're much more firm. When they're in isotonic solution, while they may not be dead, they're not as firm as they can be, and they kind of tilt over, are a little bit limp, stuff like that. We call that flaccid. And we call the term for nice and full and plump cells turgid. Now, or turgor. Turgor is the state of having extra firmness from water. Now, if your plant doesn't have enough water, or it's going to be, and they're surrounded by what's called a hypertonic solution, a very salty solution that lacks water, then as a result, the outside environment is going to draw water out of the plant cell, and it's going to lose water, and as a result, it can lose so much water that the plasma membrane begins to peel off. All right, it's a horrible arrow. But this plasma membrane right here starts to peel off the cell wall, and as a result, it can peel off to such a degree it separates completely from the cell wall, and then the plant cell can't recover, and the cell dies. So this is a more cartoony version of the last couple images, but that just kind of summarizes the difference between animal cells versus plant cells and what's ideal. So now I'm just going to give you some examples of types of problems you may come across in your future worksheets. Now let's look at this kind of mock example of a cell and an environment. So the inside of the cell is 0.05 molar and the outside environment is 0.03 molar, and you should know numbers and you should be able to tell which side is hypertonic versus hypotonic and predict how the water will flow. So guess and then play the video and I will give you the numbers. Okay, so the actual cell itself is hypertonic. It's got a higher concentration, while the outside of the beaker is hypotonic, and because the inside is more concentrated than the outside, as a result, water is going to flow into the cell, and it's going to swell up the cell and make it a little bit bigger, and if it's super extreme, it can cause the cell to burst, but it doesn't always immediately cause a cell to burst. If it's a very small difference, your cell swells up just a little bit bigger, but in extreme situations, the cell can potentially pop, right? So remember, water moves from high water to less water, but whenever there's more water, there's less solute, and whenever there's more solute, there's less water, okay? So, where will water flow? Towards the 0.2 molar concentration or the 0.8 molar concentration? And where will water flow if we talk about in terms of water, from 20% water to 80% water? So make your guess and then play the video. So in this case, when there is more solute, there's less water, so water will flow to the 0.8 molar concentration. But when we're talking about just water itself, then water will flow from more water to less water, so it'll move to this 20% water, because if it's 80% water, it's 20% solute or other stuff, and if it's 20% water, it is 80% solute. So water, again, moves towards the saltier or sugary side where there's less water. Here's another example of problems that you may come across in your worksheet, but I'm going to change the numbers a little bit because it's a little bit fuzzy here, and I want to give you some different types of questions. Okay, so looking at this, you only have the solute amounts, but just reminding you, water tends to move to the saltier side, but you should also remember that whatever there is more solute, there's less water, and vice versa. So in this case, when there's 20% solute, that means there's 80% of water. And over here, when in the cell on number 1, there's 10% solute, which means there's 90% water. Look at cell number 2. In this case, the inside cell is 30% water, while the outside of the cell is 40% water. And at this point, you should be able to predict that water moves from high concentrations of water to low concentrations of water, or wherever it's saltier. So using that, we should be able to predict that water is going to leave the cell in number 1, since it's got more solute and less water. And in this case, for number 2, water is going to enter the cell because there's more solute and less water in this case. So for number 1, the outside is hypertonic. The water, as a result, is going to move out of the cell towards the hypertonic outside, and as a result, the cell will shrink. It may shrivel, or it may only move a little bit and still be overall okay, but still going to be less big. For number 2, on the other hand, the outside is hypotonic compared to the inside. It's going to have, as a result, have the water move into the cell. And as a result, the cell will swell. Maybe you'll get to the point that it lyses, but we don't know. We just know it's going to go in and make the cell bigger. Now notice, even though we use these things, and we said the outside was hypotonic on number 1, while the outside on number 2 is hypotonic, you'll notice, hey, number 2 has a way higher concentration of stuff than number 1. That is true, but we're talking about the environment's relationship with its cell. Okay? So the terms hypertonic and hypotonic have only to do with the comparison between one thing to another. So the outside on number 1 is hypertonic when you compare it to the cell. The outside on number 2, though, even though it has a higher concentration compared to 1, we're not comparing it to number 1. We're comparing it to the cell in number 2. And the outside on number 2 is hypotonic compared to the cell in the picture for number 2. Alright, so that's it. So just reminding you, without the use of energy, materials in the universe tend to diffuse, meaning move naturally towards equilibrium. So they move from areas of high concentration to low concentration until equilibrium is reached and things are roughly equal. With water that can selectively pass through a membrane, it's going to move from high concentrations to lower concentrations of water, which means it effectively moves to higher solute concentrations in the event that the solute cannot reach equilibrium, cannot move on its own. And tonicity terms like hypotonic, hypertonic, and isotonic are used as comparison terms between two solutions, specifically in how they relate to one another. And when they're allowed the opportunity, water will move towards the more hypertonic solution. Now, in terms of biology, though, this is critical for organisms, and in animal cells and other cells that don't have cell walls, it's really important to be in isotonic environments. And some animal type cells, like protozoa that are like animals, that look and act like animals, they have strategies to cope when they're in environments that are too watery or too salty. But in general, animals are going to try to be their best by creating an environment that is isotonic or staying in an environment that's isotonic for them. However, for plants, on the other hand, they actually are best suited to hypotonic environments that allow them to take in extra water to be as big as possible, because they don't have to worry about bursting, all thanks to their cell wall. And these were the terms that were covered in the notes today, and I will talk to you guys on the next lecture. Bye.